Welcome to CAD Micro's webinar for casting industry to learn about efficient method. First of all, I'd like to introduce CAD Micro. CAD Micro is a Canadian company that has representation across the country from Vancouver, Calgary, Toronto, Cambridge, Montreal, and Quebec City, with offices and staff across the country. A couple housekeeping on the questions. You can type any questions you may have during the webinar in the question tab. We will have a question and answer period at the end. Also, the recording will be sent to each one of you after the webinar. A little bit more about CAD Micro. CAD Micro, we enable innovation. So we do help customers with the design software, advanced manufacturing, which includes additive and manufacturing, advanced simulation, 3D scanning and metrology, and AR, VR, and XR. Our team here on the metrology side I will present with you is myself, Director of the 3D Scanning Metrology at CAD Micro, and we have Shubham Kochamrota, Technical Manager in Lean Manufacturing, and we have Hardik Patel, Metrology Application Specialist. So the agenda today, we're going to cover on how to create digital twin, using the ZEISS T-Scan Hawk 2. We will review quality control of casting process using ZEISS Inspect, and then solving any casting issues using the digital assemblies. And then we'll wrap it up with some question and answers. So Shubham, the floor is yours.
Thanks, Joe, and thank you everyone for joining us today. My name is Shubham. I work as a technical manager of lean manufacturing at CAD Micro, and so I handle all the projects that are related to 3D scanning, metrology, and reverse engineering here at CAD Micro.
My name is Hardik Patel, and as Joe mentioned, I'm the metrology application specialist here at CAD Micro. So today we will be scanning this casting part using the T-Scan Hawk 2 scanner from ZEISS. So as for the hardware of the scanner, we have 2 cameras and 1 laser projector. We also have a trigger button up front, which helps with the scanning. And at the back, we have 4 more buttons, which helps with the navigation without even touching the computer. Other hardware that we have is a rotation table, which basically helps me scan from every possible angle very efficiently and easily. So we'll just jump right into scanning. So it's very simple to start scanning. I just click one of the buttons over here. So I just click one of the buttons and it takes me to this work page, which I can handle just using the scanner itself. This is basically template selection and point spacing, which is basically the resolution of the scan. I'm just going to keep everything to default for now, and then I capture the reference points. So reference points are basically points that helps the scanner determine where the scan is in space. So it basically helps with the navigation of the scanner itself. It also helps with scanning both the sides. So when I flip the part, it will use these reference points to figure out where the alignment goes. I'm just going to simply rotate the part and capture all the possible reference points that I could. Once a quick go through is done, I can just hit continue, and then I can define a background plane. So background plane, basically what it does is it forms a plane, and everything under that plane is cut off from the scan. So we will just be able to scan the part itself and not the plane, or let's say the computer screen, or like whatever's below over here out of the picture. So yeah, okay, just already get scanning. So how the scanning works is that the laser projector projects. I don't know if you guys can see it, but like it's a crisscross laser lines, 20 of them, different color, and this basically helps the camera pick up the path, and we have a scan body on the screen. So I'm easily able to go over the inside body using a rotate table, capture all the different angles that I need to capture. And then once I think it's a good enough scan, I can see that there's a hole right here which does not have enough data scanned inside. So what I can do is I can change my projection mode to a deep pocket mode. So you'll be able to see on the screen itself that only a single green laser line is visible on the screen or outside the screen. And this basically is nothing to do with accuracy, but it's just the focus of the scanner. So it helps the scanner focus more on where the deep pocket is and be able to capture data more easily. So it's basically just like using a paintbrush, going over it while looking at the software or even the card itself, getting all the good angles scanned. And once the results are satisfactory, you can just properly scan. Once the scan is captured, we can move into scanning the other side. So I'll just simply flip this. Recapture the reference points. This exact same procedure. Yeah, once that is good, I can confirm it. And then just like the previous one, I'll define the background thing so that I can cut it off. And then I can start scanning again. So this is not a shiny or a dark part that is difficult to scan, but even with those parts, the scanner makes it an easy job. Because I'll show you guys in a minute. The scanner has different scanning options. So if I go here, exposure mode, so this is default. If I go dark and shiny, the laser lines are more brighter, and that's why it's able to capture dark and shiny surfaces easily. And we also have bright surfaces where the laser lines are duller, reducing the exposure, so it's able to capture those bright surfaces as well. But for this one, default is good enough, so that's what we have right now. And I think we do have good enough data. Yeah, this should be good. So once I have good enough data, I can just confirm the scan. And then I just go on to the computer. This is the scan that we have. This is scan 2. That we just transform to 2 series. This basically uses those reference points to align both the scan files and make a preliminary mesh. So as you can see, it's aligned properly. And now I can polygonize it to make the final mesh. With polygonization, it forms triangular polygons all over the surface to create a mesh. All the overlapping polygons are checked to verify which one's a good polygon, which one's a bad one, and all the bad polygons are basically omitted. So I think we have our scan file here, which is a mesh. I can transfer now to Shubham to conduct all the inspection that we need to do here.
Thank you, Hardik. So now I'm going to show you how you can use the scan data to inspect your entire process chain in ZEISS Inspect software. Okay, I'm going to share the screen. Okay, so now that you can see my screen, this is the scan file that Hardik just passed on to me. Here you can see I have this scan file, and if we want to look at the display, like look at the mesh structure, you can see that mesh is extremely dense, especially at the curvature as compared to the flat areas where you don't need that many details. So to adjust the size of the mesh, there's the algorithm that the software uses. To turn on this mesh structure, I also have the CAD file of this part. This is the rock casting, so we are going to inspect that first. One of the main features of this casting is the diameter of this flange, because either liquid or gas is going to pass through this flange, right? So one of the important features, and we are going to inspect that first. So to inspect that, I have few elements that I have created. and I'm going to create a section. I'm going to use one of the planes to create a section. And so, and then I'm going to create a circle in there. And on that circle, I'm going to create a analysis of this flange, which basically tells me where my position is and what is the diameter of this flange. So I can clearly see that the flange is out of tolerance in negative direction. So it has negative minus 0.4 millimeter of deviation, as well as if I look at the flange on the other side, which is flange 2, it also has negative deviation. Also, when I create a surface comparison between mesh and the CAD, I can see the inner structure of the mesh, and I can clearly see that there are some deviation. It has too much material on the mesh. So if I place this deviation label, it tells me how much extra material do I have in that area. Now, that area is created using the sand core, which is responsible for casting that area. So this clearly means, this deviation clearly tells us that the deviations were passed on by a sand core. It is reasonable to say that the deviation are actually on the sand core. So for that reason, we are going to now inspect the sand core itself. We have not scanned it right now, but we already have the scan file for that. So I can show you the scan file for my sand core, which is this. So this is my sand core that I have scanned, and I also have the CAD file of this. So now when I create a surface comparison on the sand core, it gives me a color map, and I can clearly see that this is less than what it is supposed to be. It has negative deviations when it comes to the diameter, and I can see a new issue, which is this sand core marks are very short in length. So this clearly means that the deviation came from the sand core, and here we can say that there is this damage is also caused by the sand core. So now this sand core is made by the tool, which is the core box. So now we're going to inspect the core box itself. To inspect the core box, I have imported mesh of this core box right here. And then when I create a surface distance of this mesh, I can clearly see here that this core, the length of the core box itself is small. Also, there is two extra material here, which clearly means that this extra material was passed on to the sand core itself, which is basically responsible for the short diameter of the raw casting. So now 3D scanning can not only help us define and inspect the final part, but it can also help us find the root cause of what is causing those deviations. We still have to find out the cause of we still have to find out the cause of this extra material right here. This damage that was caused on the sand core. So when we create a surface distance between the sand core and the tool itself, you can clearly see that there is extra material right here. So this extra material is caused by the shooting errors during the core assembly process. So we didn't just went through inspection of the final casting, but we also saw what are causing the deviation in the final casting by analyzing each and every step in the casting process. This is the end of inspection, and now I would like to pass on to Joe for Q&A session.
Thank you, Shubham, Hardik. I know that we can expand a lot more into the casting, but this is really just a quick overview, everyone, for the capability of what you can do with this 3D scanning device and software to be able to analyze your work at hand. So I'm going to open it up to some questions. I have a couple here that are already in. All right, first question that we have is, when we were aligning your scan with the CAD data, what type of alignments can be created?
So ZEISS Inspect allows you to create different type of alignment, like mounting location alignment, which can be an RPS type, where you have different points and you want to align your part to those points and see the performance. It allows you to create local best fit alignment, where you want to check the performance of a certain area of the part when it is aligned to a certain area. It allows you to create datum alignments. So you might have datum systems in your drawings, and you can create those and then inspect your part in those alignments. So there are all type of alignments that you can create using the ZEISS Inspect software.
Okay, thank you. And what's the maximum part that can be scanned with Hawk 2?
So this scanner, first of all, it comes with an inbuilt photogrammetry. So there is no real limit which you can scan with. You can scan a part as small as that can fit in your hand to as big as a car using the photogrammetry equipment without compromising any accuracy.
Okay, good. And one more, can you inspect without having any CAD file?
Yes, you can. You can simply bring in your mesh in the software and create all the elements that I just created without using any CAD file. And just enter the tolerances using a drawing, and it will give you deviation between your drawing value and mesh value.
Okay, good. And one more, you are using a rotary table. Like, do you have to use a rotary table?
Not really. This rotary table comes in handy for part which fits on the table. But if you want to just place this part on any generic table, you can place on the reference dot, which Hardik mentioned during scanning, directly on the table, and place the part in between them and scan.
Okay. Well, thank you for everyone for attending our webinar. And if you have any questions or would like to know more, please don't hesitate to reach out to our team here at CAD Micro. We'll be happy to help you with your project. Thank you.
Thank you.
Thank you.